In section 8.4, we're going to be working on defining polar coordinates and graphs. Our objectives are going to be to graph points given their polar coordinates, to convert between rectangular coordinates and polar coordinates and vice versa, and to convert between rectangular equations, polar equations, and vice versa, and then to graph in graph polar equations. So as we start here, warming up, the standard XYZ coordinate system makes plenty of sense for thinking and communicating in 3 dimensions in some contexts, but does not always work well for real life situations. So first I want to consider what we mean by XYZ. We typically think about it with a 2-dimensional graph where we graph things in X and Y, and we'll count along the positive X-axis and the positive Y-axis. If we graph in 3 dimensions, we'll think about where our X and Y axes are, and then our Z axis is understood to be perpendicular to those, coming straight out of the ground, and it's drawn as representation this way. So we're not going to be working in 3 dimensions right now, but since X, Y, and Z were mentioned, I wanted to talk about those 3 dimensions. We are going to be primarily speaking in terms of 2 dimensions, and I should say only speaking in terms of 2 dimensions aside from this one page here, but we want to convert that into this idea of polar. So in terms of 2 dimensions, or 3 for some of these examples, if you needed to locate the position of something like a fly in the classroom, and if you think about this without height as an issue right here, if you have a fly in a position, you would not count, well, it happens to be 7 inches or so over to the right, and then a measurement of 4 or 5 inches up to the top, and you wouldn't use that kind of system or a grid to define where its position is. So I don't know how I counted here, 1, 2, 3, 4, 5, 6, 6 and 4. So you wouldn't very easily describe it as, if you walk 6 paces to the left and 4 up, you'll find the fly. That's not what you would do. Instead, if you had that fly in that same position, you're just going to point at it, and it's over there. And that pointing at the fly is going to be defined by the angle at which you've lifted your arm, and then a distance measurement along that path to get to the fly. So instead of talking about this in terms of left-right or XY coordinates, we would talk about this in terms of distance and position, or distance and angle. And that is really the basis of what we're going to be doing with the polar coordinate system. Locating a fly is just one example. Locating the position of a ship on the oceans, again, angle and distance are going to be more efficient when you're on the ocean than trying to figure out how many steps south and how many steps east of a certain position it is. We're going to think more in terms of angle and distance to locate that extra position here. Same thing for constellations in the sky or slices of an MRI. So for all of these, we need that alternative to the rectilinear or rectangular coordinate system, which are our XY or XYZ coordinates. Let's define those on the next page. So on our next page here is where we begin defining and discussing polar coordinates. These are the coordinates for locating a position. It's just like rectangular coordinates in that we're starting in 2 space, XY plane, but we're going to find its location based on the relation to the origin. And so we're going to be looking at position, like we said, based on distance and angle. So the distance, we'll use r just for the radius of that length right there. We can imagine a circle, like the unit circle, doesn't have to be of distance 1 there. And we're thinking about that relationship between like trigonometry in terms of the circles, in terms of ordered pairs here with angles and distances. So the origin point on the coordinate system is also referred to as the pole. Pole. And that's partly where the name polar coordinates gets its name. The origin is called the pole. Angles are always measured counterclockwise, just like they are in the regular trigonometry system that we've used before. So they're measured counterclockwise. From the x-axis, or the x-axis is also called the polar axis. So instead of labeling that x-axis as x, it's just going to be our polar axis. We're going to measure everything in relation to that axis. To plot points on a polar graph, polar graphs are usually plotted on a grid of concentric circles, like this polar grid down here, where the spokes mark off specific angles. So these are marking off specific angles. These are the spokes. And 0 radians or 0 degrees is what we normally call the positive direction. And polar coordinates in 2D are going to be stated as ordered pairs of the form r comma theta. I mentioned this as distance comma angle. The distance is going to be r for standing in for radius, that is our distance, and theta is the angle. So it is of that form, distance comma angle. As we mentioned earlier, r comma theta is our distance comma angle. And in that, angle, again, is measured from the positive x-axis, counterclockwise, just like a typical positive measurement of angle. Then in step 4, so we're going to locate the angle. We're plotting a point, locate the angle, measured from the x-axis, and then move a distance r from the pole, depending on the sign of r. So if the r value is positive, you're going to move outward from the pole along the directed angle. And if the r value is negative, you're going to move outward from the pole in the direction opposite to the directed angle. We've got a few of these here with positive and with negative r values, so we're going to get a chance to look at multiple polar coordinates here. All right. Okay, so this is my positive axis. So let me just highlight this right here. Positive axis. So this is where we're going to start. That's where the x-axis would be if we did imagine a grid running through this. And that's where the angle 0 is going to be, either in radians or degrees. And we know this would be pi halves. So it looks like these are markers that are by 12ths. So that's where pi sixths or 30 degrees would be. That's pi fourths or 45, pi thirds or 60 degrees. And then this is just another marker for the 15 more degrees, right? Each of these would be 15, 30, 45, 60, 75, 90. So each of these is either 15 degrees or pi 12ths. And so we're going to count our angles around those spokes, and we're going to count our distances along the inner circles at the distance of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. I'm going to need to count by ones, it looks like, to fit most of these in here. So I do have a negative 10 I'm going to need to graph. I was hoping I could count by 2s, but they're just not going to be big enough. So if I have anything that has a 1, it's going to be real tight in there on that first circle. Okay. I'm not going to label these 1, 2, 3, 4, 5 because there's not enough space for those labels to show up nicely. So we're going to just notice that each of these is a distance of 1. So I'm just going to make a mark near the outer edge that each of these is a distance of 1 unit out. So that's what I'm trying to indicate there. That's a distance of 1 measurement out. Okay. So the first point I want to plot needs to be at a distance of 3 and an angle of 60. So this is my 60-degree angle, right? 15, 30, 45, 60. And I need to be 3 out. So that's 1, 2, 3 out. So right there would be the angle for point A. Let's graph the angle for point B. The angle for point B is going to be at a distance of 0 and an angle of 45 degrees. So this is where 45 degrees would be, but I'm not going to travel any distance. So I'm actually going to stay right there at the origin. That's point B. So it is interesting to note that the point 0, 45 is equal to the point 0, 0, because, or 0, 80 or 0, 100. The angle doesn't matter if the distance is 0. All of the points are going to be coinciding at the same point if the distance is 0. Okay, the point C. So we need to go up 120 degrees. So this is 90. So 90 plus 15 would be 105, plus 15 would be 120. This is where 120 degrees is. And if I go along this angle out 5, the point over here out 5 would be 5 in the positive direction. But because I have a negative 5 distance, I need to go along this angle in the negative direction. So let's just line up right here. We're looking at this angle. If I trace straight through the origin, the pole, I need to go 5 in the negative direction. So 1, 2, 3, 4, 5. That is going to be the point C. All right, so the point C on the angle 120, but backwards 5 puts us here. I could write that if I wanted to with a different angular measure. So this would be at the angle 300 degrees if you count all the way around that circle. So this is the same as the point that goes 5 in the positive direction on the angle 300 degrees, but backwards 5 on the angle 120 degrees. I know it's 300. If I add enough 15s, that's where I'm going to end up. I also know it's 300 because this is a 60-degree gap to 180, so I need a 60-degree gap to 360, of course. So 360 minus 60 gave me the 300. Okay, so plotting in polar coordinates takes a little bit more thought than plotting in the x and y coordinates. We need to think about both the direction and the angle. Let's continue and look at the next one. Point D. Point D needs to have an angle that is negative 60 degrees. So negative 60 degrees, negative 15, negative 30, negative 45, negative 60. That's going to be coterminal with positive 300. So this is where negative 60 degrees is. And I need to be backward 7. So 1, 2, 3, 4, 5, 6, 7. Backwards angle and backwards distance. This is where point D will end up. That is a perfectly fine way to describe where it is at negative 7, negative 60. But if I did wish to use positive values, that would be coterminal with the angle 120. So this would be at positive 7, positive 120. Just writing in that as an alternate way of phrasing point D. Instead of a backwards angle, backwards direction, I could use a positive angle, positive direction. Same point. Now, points A, B, C, and D were given in degree measure. Point E is given in radian measure. The angle is 3 pi over 2, so we know that that is the angle down here, 3 pi over 2. And it's got a positive, so along it, this is going to be point E. Out 2 along the 3 pi over 2 angle. And the last one is going to be 10, pi thirds. So pi thirds is the same as our 60-degree angle up here. That's just the radian measure for this angle. So out 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is going to be point F Again, it's listed. Oh, I'm mistaken. That's not point F. I didn't see the negative. So there is a negative on that 10. That point that I listed right here would have been for positive 10. I just missed the negative when I first glanced at it. So in this angle, we need to count backwards 10. Now that I've seen the negative there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there is our angle F with the negative 10 for its distance. So I could write that as a positive if I were able to come up with the coordinates for this point, remembering that that is pi. So if I go pi thirds past pi, this would be where 4 pi thirds is. So this would be, with positive measure, 10 comma 4 pi thirds would be an angle that lands in the same point using positive values. Okay, lots of examples here in graphing in polar coordinates. Let's take a look at our next page. We can use our knowledge of rectangular coordinates to define polar coordinates. We're going to start by creating a basic point with coordinates expressed in polar and rectangular. So we're going to have this point here, x comma y, or r comma theta, the same point. It can be defined in either of those two coordinates. And if it is, let's draw here. If it is, I'm going to make myself a triangle. In terms of x, y, x would be the distance that we traveled across the x-axis, and y would be the distance that we traveled up from the y-axis. So I would label these two positions, x and y. But I can also label r as the distance from the pole, and I can label theta as the angle from the polar axis. So I've made myself a triangle here, and we can start expressing some relationships. One of the relationships is based on the Pythagorean theorem. We can say that we know that x squared plus y squared is equal to r squared. That's because this is certainly a right triangle. We can also say that we know that the sine of theta is equal to y over r, and the cosine of theta is equal to x over r. And we could even use the tangent of theta to relate y over x. That should be most combinations. We could use the secant cosecant functions if needed, but we're going to be just duplicating or using reciprocal functions for the ones we've already got here. So we can use these in order to convert coordinates from rectangular to polar or vice versa. So here I have coordinates that are in rectangular. So these are in x and y. If I'm in x and y and I want to find r and theta, I'm going to be able to use the Pythagorean theorem in order to solve for r. And then I'm going to be able to use the tangent, or actually arc tangent, if we get theta by itself. Theta would be equal to arc tangent of y over x in order to solve for theta. So this is how we're going to be able to solve for both r and theta if we know x and y. So here we go. We are in x and y. We're in rectangular coordinate system. We want to convert into polar. So this is currently a pair of xy coordinates. The x value is 3 and the y value is also 3. So when I find r, I know that 3 squared plus 3 squared is equal to r squared. So that's 9 plus 9 equals r squared. So 18 is equal to r squared. and the square root of 18 would be our r value. We can separate that into square root of 9, square root of 2. Square root of 9 is 3 times the square root of 2. So I can find the exact value of r as 3 times the square root of 2. And then I can find the theta value with the arctangent of y over x. So that's the arctangent of 3 over 3, or the arctangent or inverse tangent of 1. And if I remember from the unit circle, I'm going to have an arctangent that is 1. Anytime I have an angle that is either 45 degrees or pi fourths, because the x and y coordinates are equal. So that's going to happen here at pi fourths. Or it could happen down here as well, because tangent is positive in both quadrants 1 and 3. But this is, of course, too big to fit inside of a singular triangle, and obviously it doesn't match up with the coordinates 3 and 3, which are in quadrant 1. So we're going to be up here at this angle. If we happened to have an arctangent of 1, but we knew our ordered pair was in quadrant 3, we'd go ahead and find this angle as well. So it's additionally important for us to know which quadrant we're working in when we're trying to find the angle. So the angle is going to be, you can either write this in degrees or radians. I'm going to go ahead and put mine in radians. So it's pi fourths, or you could have said 45 degrees, making this ordered pair 3 times the square root of 2, comma, pi fourths in radians. Okay, we're going to do this again here for part B. This is again the rectangular coordinates. So I'm given the values of x and y. I need to find the r value. So we're going to take 2 square root of 3 squared plus negative 2 squared. And that is equal to r squared. We're going to solve for r. 2 square root of 3 squared, that's 4 times 3, plus 2 squared, that's 4, equals r squared. So that's 12 plus 4 equals r squared. So 16 is r squared. So we're going to take the square root of 16. So our r value is 4. When we go for the angle, we're going to need the arctangent of the y value, negative 2, divided by the x value of 2 over the square root of 3. And that's the arctan of negative 1 over the square root of 3, or that does rationalize to negative square root of 3 over 3. If you have a chart in your notes that has arctangent values for quadrant 1, you can look that up. I'm going to pull out mine. In my formula sheets, I can see that the tangent is equal to square root of 3 over 3 for a reference angle of 30 degrees or pi sixths. So let me make a quick note of that. Again, I'm going to work in radians. So for the angle pi sixths, this would have a tangent value that was the positive square root of 3 over 3. The answer that I'm looking for is not going to have a positive tangent. It's going to have a negative tangent. So tangent is going to be negative in quadrants 2 and 4, because that's where sine and cosine are opposite. They're both positive in quadrant 1. Sine and cosine are both negative in quadrant 2. So when you divide two negatives, you get a positive. So the tangent value is also positive in quadrant 3. Now, considering the position for this particular point, the x-coordinate is positive and the y-coordinate is negative, I know that I need to be in quadrant 4. So I'm looking for the angle down here that is going to have a reference angle that is pi sixths. I can use, for that angle, I can use the angle negative pi sixth. That's the shortest way to refer to this angle is by going in the negative direction. Or if I wanted the positive angle for that, I could go around and say that it is short of 2 pi by 1 pi sixth. So that would be at 11 pi sixths. So I can write this ordered pair as, for example, I could say 4 for the distance, comma the angle negative pi sixths, or I could say 4 for the distance and 11 pi sixths. There's not just one way to write it. I'm going to go with this first one just as the simpler way to write it. However, I could go in a different direction. Like I could go with 5 pi sixths, but use a negative 4. So if I used negative 4 in the angle 5 pi sixths, that would still have me counting across the opposite down to this point here. So the points are not unique represented in polar coordinates because we're able to represent any angle multiple ways with coterminal angles. Now we're going to work on converting these angles, these points here that are in polar coordinates back into their rectangular coordinates. All right, so we previously converted in to polar. Now I'm going to convert in to rectangular. Here, what I'm going to be given is the r and theta value. So if I know the r and theta value, we are going to be able to use these two lines here to find the x and y. Multiplying r over gives us r times sine of theta is equal to y, and r times cosine of theta is equal to x. So these are going to be the two tools that we are going to use if I know what r and theta are and I need to find the x and y values. If I know that r is 10 and the angle is pi thirds, the x coordinate is going to be found with r, 10, times the cosine of pi thirds. And based on the unit circle and the location of pi thirds has coordinates on the unit circle, 1/2, comma square root of 3 over 2. So the cosine value is 1/2. That's 10 times 1/2, which is 5. And the y value is going to be r, 10, times the sine of the angle pi thirds. That's the y coordinate of that ordered pair. So that's going to be root 3 over 2. That's 10 times square root of 3 over 2. 10 divided by 2 is 5 times the square root of 3. So in x and y, this ordered pair is going to be 5, comma, 5 times the square root of 3. For part B, these are again values in terms of r and theta. So if I know the r value is -5 and the angle value is 135, I can find the x coordinate by taking r, -5, times the cosine of 135 degrees. 135 degrees sounds like it might be on the unit circle. So if we consider the position on the unit circle, we know we have 45 degrees. We've got our 90 degrees, and then 135 degrees would be in the center there of quadrant 2. So the cosine value is going to be, the x-coordinate over here is negative. So it's negative root 2 over 2, comma the y value is positive root 2 over 2. So I will have negative 5 times negative square root of 2 over 2. That comes out as positive 5 square root of 2 over 2. And our y-coordinate in negative 5 times the sine of 135 degrees, it's going to be negative 5 times that positive square root of 2 over 2. That'll come out as negative 5 square root of 2 over 2. So the answer here would be the ordered pair 5 square root of 2 over 2, comma negative 5 square root of 2 over 2. I want to talk about a quadrant here for a second before we move on. What quadrant was this original point in? This original point had an angle of 135 degrees, which does put it in quadrant 2, but its measure was negative. So it would have ended up as an angle in quadrant 4 because the radius measurement was negative. So this angle down here with a positive x and a negative y, this point here is in quadrant 4. So it's going to match up with the location of the point in radian coordinates, in polar coordinates up there, in polar coordinates and then now in rectangular coordinates. Okay. For the next topic, we're going to take polar and rectangular equations and look at converting those into their other format as well. The relationship between polar and rectangular coordinates translates into some very interesting differences between equations in the two systems. Sometimes a complicated curve in one system is easily described in the other, and vice versa. Let's convert each of these following rectangular equations into polar equations. When we convert things into polar, we're going to use the same equations we were using on the previous page when we converted our points into polar. We're going to be taking x and y, converting them into r or into theta. So we can get all things in terms of r and theta. In this instance, what I have is x squared plus y squared equals 25. And I know that x squared plus y squared is equal to r squared. So I'm able to replace x squared plus y squared with r squared. R squared equals 25. And if I solve for r, that's going to give me r equals positive and negative the square root of 25. So I get r equals positive and negative 5. If I think about this pair of equations, r equals positive 5 would be a circle. There's no theta value defined. So you're going to trace along this circle in the positive direction for all theta. R equals negative 5 would just trace around that same circle backwards. So you're going to get the same picture twice. So it's duplication of the same graph. I don't need to list them both. So this simplifies as just r equals 5. I can actually check these using the decimals calculator. Unlike the ordered pairs, decimals does not yet have the capability for graphing ordered pairs in polar, but it does have the capability for graphing equations. So let's take a look at the original equation. X squared plus y squared equals 25. That's the equation of a circle who has radius 5. And if I look at the equation r equals 5, That's the same circle with radius 5. I can have them both showing up and one covers the other. So entering r equals 5 is understood to be that same circle. If I did look at r equals negative 5, the graph is the same. It just is the circle graphed in the opposite direction. So I don't need both. Any one of them is going to match the graph of the original. The full original graph is graphed by either of those. We're just selecting to use the positive one as the simpler way to express this graph. This is an instance where writing the equation of a circle is easier to do in polar coordinates, just need to say r equals 5, than it is to do in rectangular coordinates where you need to say x squared plus y squared equals 25. Okay, let's take a look at the next one. In the next one, we have 2x minus y equals 5. Now, I don't have x squared and y squared, so I'm not going to be able to do a direct substitution with this line, but I could go backwards here instead. If I have y, I can plug in r sine theta, and if I have x, I can plug in r cosine theta. So 2 times x, that's r cosine theta, minus y, that's r sine theta, that's equal to 5. I could factor r out here. This is r times 2 cosine theta minus sine theta equals 5. And typically, just like typically in x and y, we solve our equations for y, which was not done here. Typically, we solve polar equations for r if that's possible. So I'm going to solve for r. R equals 5 divided by 2 cosine theta minus sine theta. So this is going to be our equation expressed in terms of polar, in terms of the variables r and theta. Let me just take this equation in its original form real quick and solve for y, which is pretty typical in x and y. So if I get the y onto the right-hand side, I have 2x minus 5 equals y. And from there, I can tell this is the equation of a line. So this should graph as a line. Let's take a look at it on Desmos. Clear up the old graph here. In its original form, 2x minus y equals 5. Looks like a line. Sounds good. And if I graph r equals 5 divided by 2 times the cosine of theta. I'm spelling out the Greek word theta to make that theta symbol appear. It's spelled Theta. As soon as I finish the A on theta, not in a note, it changes to that symbol. And then I've got the sine of theta as well. Hey, the line is the same, as you can see. So if I dot this one, we'll see they're lining up in the same position. This is an instance where that equation looks a lot prettier in rectangular coordinates than it does in polar coordinates. So we've seen one example so far of each. This looks better in polar. That one did not. That one looks better in rectangular. But we were able to write it in polar. That's a line. Now we're going to convert in the other direction. We're going to take things that are in polar and we're going to convert back into rectangular. One of them, we've got an r equals 4. I don't have a way of getting just r, but I do have a way of getting r squared. So if I square both sides, r squared equals 4 squared, or r squared equals 16. Then I can replace r squared with x squared plus y squared. So we're going to do that. X squared plus y squared equals 16. This one's very similar to part A above. R equals 4, R equals 5. They're both circles. So this circle would look like x squared plus y squared equals 16 in rectangular coordinates. For our cosine theta, we can actually sub in x, right, for our cosine theta. So x is equal to 6 would be this equation. So just to make a note of what kind of equations these are, just kind of cool. That's going to be a circle. This is going to be a vertical line. Okay, I didn't graph this one because I already did a circle earlier, but I'll graph part B. In part B, we would graph r cosine theta equals 6, like a vertical line, or I can graph x equals 6, of course, that same vertical line. The interesting difference about these is, yes, that is simpler to write in terms of x and y, in terms of rectangular coordinates, but it's not a function in rectangular coordinates. It is a function in polar coordinates because each distinct theta gives a separate distinct r value. So there are things that, just like the circle is not a function in rectangular coordinates. It is a function in polar coordinates. So that distinction is going to allow us to do some things with polar coordinates that we're not able to do in rectangular. One more here to look at. Here I have r equals 2 cosine theta times 3 sine theta. Unlike the last one, I don't have an r cosine theta that I can replace with x. As a matter of fact, the only r is on the other side. But if I needed to get an r cosine theta, could I multiply both sides by r? That would give me r times r is r squared equals 2r cosine theta plus 3r sine theta. Now we're going to be able to make some replacements. We know what to sub in for r squared. That's x squared plus y squared. I know what to sub in for r cosine theta. That's x, so 2x. And I also know what to sub in for r sine theta. That's going to be y. So we've got our 2x plus 3y. So this would be our equation in rectangular coordinates. You may recognize that one, you may not. It's similar to our circle, but with those extra coordinates, it's not in standard form for a circle. Right now, I need to complete the square. So it's a circle whose center is not at the origin. Let's take a look by graphing. The initial form was r equals 2 cosine theta plus 3 sine theta. It's a circle, and its center is not at the origin. It's not in standard form for a circle and rectangular yet, but if we write it, we can see that the two equations do match up. And if we did want to find the center of the circle in rectangular coordinates, we could get everything on one side and complete the square and so on in order to find that center. It looks like it's not at a whole numbered value, at least as far as where the x coordinate is. So we would need to work to find that. All right. But right now that is the equation, just not in standard form for that circle. Topic number 3 has us looking at more graphs that are in polar coordinates. Just as with rectangular coordinates, we can make a table of values in order to begin thinking about what graphs look like. In a way, we're simply asking how far out from the origin to plot a point for any given angle. We can also graph things in polar mode in the calculator. So I have been graphing these. Polar mode is not needed for Desmos. It understands when I use r and theta to graph things polar. What polar mode can do is there's a polar option in I just need to make this a little bigger so I can see. Polar, oh, it's actually right here. So instead of having my grid rectangular, I can click on this grid, which is circular, and now I can see the way that my object would look like on a polar grid. So my grid becomes this polar scale right here instead. So that's by just changing the grid, Decimals understands automatically no matter what the grid is. You can graph things using either coordinate set, using either XY grid or an R theta circular grid. So we'll make use of that to see how things look. Okay, so let's take a look at this next equation. Verify the graph if equations 4b and 5b look the same when we converted the equations. I think we've already done that. So I was already graphing those. So we will skip down to example 7 as we've already done number 6 there. Number 7, we need to start by predicting the shape of the graph before sketching it. All right. Well, I know when I see r equals 3 from seeing things like this before, we have a fixed radius where the angle can be anything. I'm going to predict that that's going to be a circle. And I can even say it's going to be a circle with radius 3. And it should be centered at the origin. So if we graph this one, let's just clear this. I'm going to put the polar grid on, and we're going to graph that r equals 3. Circle there, radius 3. So if I make this a little bigger, I can force the scale if I needed to have 3 show up, but right now it's showing just 2 and 4 and 6, so that's 3. Okay, so circle, radius 3 on this grid here. Notice that it is saying 2, 2, 2, 2. It's not saying 2 and negative 2, like you would expect to see for an x-axis, where this would be on the positive direction, this would be the negative direction. It doesn't say that because this 2 is a radial value, and radial values are positive all the way around the circle. So that's something kind of cool to see on this grid here. Okay, so that matches what my expectations were based on what we saw in examples 4 and 5. Now this next one, r equals 5 sine theta. Okay, I am going to predict that this is going to be a circle not centered at the origin. And I'm thinking that because of what we did with part C here, where if we had an r and a sine theta, we multiplied both sides by r. That gave us the x squared, y squared. And then we had some y's left over. So it's going to be a circle, maybe not centered at the origin. That's my prediction for the shape. So it's going to be a circle, and it's not centered at the origin. For this one, I guess I didn't note, but I will go ahead and say that it was centered at the origin or at the pole. Let's see if that prediction holds true. If we're looking at r equals 5 times the sine of theta, that's a circle that is not centered at the origin. Because it didn't have both a sine and a cosine, the cosine was the x coordinate. The x value is still centered around 0, but the y coordinate is not based on that value here. So it is just got an up shift to that circle. Even more things we could have guessed. And this one, you might be thinking about something similar, but that's not a cosine. That is a cosecant. So if I manipulate this for a second, r equals 2 cosecant. That's 2 times 1 over sine of theta. I could actually multiply my sine theta to the other side. Our sine theta equals 2. And r sine theta is equal to y equals 2. So I'm suspecting this is going to be a horizontal line. And let's graph it just to confirm. R equals 2 cosecant of theta. It's a horizontal line through the y value 2. Okay. Some types of polar graphs are so lovely and interesting that they have their own names. There are the cartoids. Let's look at some graphs of these just for example. I'm going to resize this graph over here and scoot my page over. The cartoid, I'm going to make this a little bigger so I'll be able to see. We'll go home on it. All right, so a cartoid equation might look like 1 minus the sine of theta. So it's called a cartoid because the graph looks a little bit like a heart. So in our example graph, we're seeing this heart shape for a cartoid. The next one's a cissoid, and that equation looks like r equals the sine of theta times the tan of theta. Now, for this one, it's going to give me an error if I don't use parentheses because it's unable to tell if the tangent is inside the theta or not. So let me use parentheses around sine of theta and tan of theta. Otherwise, it's unable to graph it for me. In particular, that first parentheses set was needed so we could determine, the calculator could determine if theta was the singular input or if the input of sine was both theta and tan. It is supposed to be sine of theta, stop, tan of theta, stop. So the parentheses are supposed to be around the angle. This is a really interesting shape though. It is this sideways thing like this that pinches in towards the origin there. And it's something that's definitely not a function in terms of x and y, but again, it is a function in terms of r and theta. Okay, the next one is called the spiral of Archimedes. So if I look at its graph, r equals 3 times theta. If I zoom out on this, you can see that spiral shape happening. And so r gets to be 3 times the angle. So as our angle gets bigger and bigger, so does our r. The next one's called a logarithmic spiral. This graph is e to the theta. And then over 10, the over 10 just makes it happen a little faster than it might otherwise. And so it's a little tighter of a spiral than Archimedes' spiral. And then this next one, strophoid, is found by taking the cosine of 2 theta times the secant of theta. I'm going to zoom in a little bit on this one because it looks a little like it might have been similar to this one, but it does flip over. So it's going to do this in its graph. So it's another interesting shape for that graph. And then a couple more interesting ones. There's the peanut. You can probably predict what that's going to look like. Cosine of 2 theta minus 2. Looks like a peanut. The twisted sister. Just see 2 more examples here. We've got the sine of 2 times theta, plus the cosine of theta, like a little twisted pretzel shape here. Okay, so it spins out, spins over, Spins down, spins up. If you can draw that, mine's not perfectly symmetric, but you can see the one on the screen looks a little better there. And the last one is a semicubial parabola. Let's see what that shape looks like. 1/4 of tan squared of theta times secant of theta. Okay, so I've entered that. Doesn't look as interesting as I was hoping. It looks very similar to the cissoid, but it's going to have some different properties to it based on this graph. So that's what it looks like right here. Some weird shape like this. Okay, so again, these shapes have been interesting to people over the 8 years, and so they got their own names. In example 8, our last piece here asks, why are the polar coordinates useful for mobile phone companies and radar operators? Well, if you have a cell phone tower, you're going to be measuring your service area by thinking about it in terms of concentric rings around that tower, right? You're going to think about your towers, and certain distances to the towers are going to have stronger signal strength than further distances. So everything's going to be radially positioned, right? So just a diagram here to show our radial positioning, circular positioning for mobile phones and radar operators, same idea. We're thinking about those circular positioning. So I'll just make a note. They both use circular positioning. So working in one of those fields or doing research on one of those things is going to require an understanding of polar coordinate systems.